So today I'm going to be talking about atmospheric rivers, or sometimes called rivers in the sky, sometimes also called drought busters, which you'll see why in just a few slides. So this is work being done in my group at NCAR, the Climate Change Prediction Group, mostly by Christine Shields. But first, I want to talk about our progress on blue waters over the past year. So the past 2 years I've come to this meeting and I've put the slide up to show you the family of simulations that we're working on. And I've always said it's going to be such a great resource that we're going to have once we get all of these finished, but we've been in various stages of getting it finished. I'm putting it up now, and I am quite excited to tell you that we're almost done with all of these simulations. So the family that I've been talking about are these quarter-degree atmosphere land-only runs. So these are AMIP style type runs. These were actually completed a year or two ago at this point. We have 4 present-day simulations and 8 future scenarios. And then we also have fully coupled runs. What is this? So here we have quarter-degree atmosphere coupled to a 1-degree ocean, and we also have quarter-degree atmosphere coupled to a 1/10 of a degree ocean. Now these, you can see we have many fewer simulations because these are extremely expensive to run. It also takes a really long time to get this resolution through a machine. So we do have a control, we have a 20th century historical, and 1 future scenario. These were actually running on blue waters this past year and finished a couple of months ago. This set of simulations, we have more. We have a pre-industrial control. We actually have some climate sensitivity runs, so where CO2 is increased 1% per year, or you have an abrupt 4 times CO2 change. And then we have 3 historical simulations, and then we use the bracketing scenario, so the lowest emission scenario and the highest emission scenario, and we have 3 of those, so 3 ensemble members each. These are running right now on blue waters, and we expect that they'll be complete within 2 to 3 months. This set of simulations is really here just for this particular presentation. These were run many years ago on a different machine, but they were used extensively to look at atmospheric rivers. And so these are a 1/2 degree atmosphere land coupled to a 1 degree ocean sea ice. And you can see we have quite a full set of simulations with those. So this really is going to be such a great resource because people are going to be able to do studies on looking at the configuration, so what coupling, looking at the uncoupled versus coupled, and then you can look at having the same ocean resolution but going from a 1/2 degree to a 1/4 degree atmosphere, and then you can look at what changing the ocean resolution can do. And this is really why I picked this particular project, the Atmospheric Rivers Project, to talk about today, is because it's actually, that study has looked at atmospheric rivers in all 4 sets of these simulations. Okay, so what is an atmospheric river? So these are a couple of graphics from observational products. On the left-hand side, this is from the EarthWind app. It's 3-hourly precipitation, which is the white colors, overlain on 850 millibar winds, and those are kind of these, you can't really see the vectors, but that's what those are. So the atmospheric rivers are a subset of mid-latitude storms, and they tap into the moisture in the tropics and can bring them up into the mid-latitude. So that's these kind of streamer type features that you're seeing on this map. And then this is just kind of zooming in on the Pacific Ocean in a product from NOAA, and this is showing the moisture in the atmosphere. And so here's one of those atmospheric rivers streaming the moisture from the tropics into the mid-latitudes. And this particular atmospheric river made landfall and dropped 625 millimeters of rain in 72 hours. And so these particular features are really important for the water supply for different regions. Also, they can lead to floods, landslides, things like that, or mudslides, sorry. And so they're really important to understand kind of how they work and then also how they might change in the future. So they really can make or break the water supply for a particular region. And we have an example of that happened in the year 2017. So this is a product that comes from the Center for Western Weather and Water Extremes, and what you're seeing, the lines here are showing you each landfalling atmospheric river over the year 2017, and they're color-coded by the severity. So there was an anomalously high number of atmospheric rivers in 2017. There were 49, and about 1/3 of them were rated to be strong or extreme. So the impact on the western states, here is the drought index. So if we look in 2016, much of the western states were in some kind of drought category, with California really being in this exceptional and extreme drought conditions. After those 49 atmospheric rivers, we look in April of 2017, and pretty much the entire region is not in a drought conditions. So these really do have a huge impact. And now I want to show you, so we're moving into the model world. So I should have mentioned that the model simulations we're looking at are using the Community Earth System model, or the CESM. And so let's see if I can get, actually I'm not even going to try it. This was an animation, but what I wanted to really show you here is how the model captures these features. And if it were animating, you'd really see the dynamic nature of them and how they can kind of move in latitude. They make landfall at different places. We have them in all of the ocean basins. And the top panel that you're seeing here is from a present day simulation, and the bottom panel is from a future simulation. So the thing that really stands out is how much more moisture is in the atmosphere in the future than in the present day. And so another question that you can ask is, how is that going to impact the amount of moisture that these atmospheric rivers can carry in the future? That's not something that we've been able to do or have gotten to with the CESM, but it is an interesting question that we will be looking at in the future. In this study, atmospheric rivers are categorized in the North Pacific and North Atlantic Ocean, and they're categorized by where they make landfall. So we have pulled out the areas of the Pacific Northwest, the California coast, the United Kingdom, and the Iberian Peninsula. That's not good. Oh, here we go. Good. Okay, so the definition that was used for atmospheric rivers in this study was the relative threshold technique that was developed by Zhu and Newell. Here's the equation that's used. Mean here is the zonal mean, and really what this equation is doing is it's looking at each latitude band and it's finding the maximum total precipitable water in the atmosphere. So it's pulling out features that might be atmospheric rivers. And then there are other criteria that have to be met. So for example, there are shape thresholds. So the feature has to be twice as long as it is wide. And then it also has to be at least 200 kilometers in length. And then depending upon which area that you're looking at, there are different thresholds for wind speed and also the direction of the wind speed. So now how does the model do compared to observations? So this is looking at a climatology, so and the number of atmospheric rivers that you would find in each month. And so the bars you're seeing here are the count, or the number of atmospheric rivers. The open bars with the hashes are observations. The dark colors are the half-degree model, and the lighter colors are the quarter-degree model, both of them coupled to a 1-degree ocean. The first thing I want to point out is that you can see that you have active seasons and sort of non-active seasons for atmospheric rivers. For the most part, it's kind of fall all the way through spring. For California, it's more in the winter months. But the resolution actually does improve. Increasing resolution improves the representation of the climatology. So in California, the Iberian Peninsula, and the UK, for the most part, the half-degree model overestimates the number of atmospheric rivers per month. And then if you use the quarter degree, the quarter degree reduces that number, and so brings it more into line with what we find in observations. In the Pacific Northwest, it's a different picture. So here, in pretty much all of the months, the quarter degree model increases the number of atmospheric rivers over the half-degree model. And then in these seasons where it's less, atmospheric rivers are less active, you can see that both resolutions greatly underestimate the number of atmospheric rivers. And atmospheric rivers have been tied to what's happening, oops. All right, Okay, well, I'll talk about this one. I think the next one might be what I was going to say. So now we're looking at what might happen in the future. And so here we're just looking at the ones making landfall in the UK and California coast. So again, this is that the top panels are the climatology that we were just looking at. And then the bottom panels are the change that you might expect in the future with atmospheric rivers. And they're tallied over 5 years. So what this is saying, if we pick January, in the United Kingdom, it's saying that there would be 6 more atmospheric rivers in January over a 5-year period. And so you can see in both of these cases, the largest changes are happening in the most active seasons. And the different bars here, actually, the different ensemble members, so 3 different ensemble members were used here. So of course, where all of them agree in the sign, we have more confidence in that particular change. So I was mentioning that atmospheric rivers respond to changes in the wind, and changes in the wind are also dependent upon resolution. And so the differences that we saw between the quarter degree and the half degree based on resolution are really being driven by what the differences in the wind field between those 2 resolutions. So here I'm showing you the wind field, so we have the vectors and then the colors of the magnitude of the wind. This is from the quarter degree coupled to the 1 degree ocean, and then this is the difference between the quarter degree and the half degree. So wherever it's positive, the quarter degree has stronger winds. And so when we were looking at the west coast of the US, we saw that in all of the regions, that the Pacific Northwest was different from the other regions in that you had an increase in atmospheric rivers in the quarter degree over the half degree. And that's because you have an increase in the winds. So it's kind of your steering flow and where that atmospheric river might make landfall is being driven by the winds. And so the reason that we saw a decrease in the other areas is because in the quarter degree there's a decrease in the winds over those regions compared to the half degree model. Okay, so now in looking at the future changes in atmospheric rivers and tying those to how the winds might change in the future, we're looking at 300 millibar winds. Here we're looking just over the Pacific, so just for comparison, this is what we see in observations. And this is the December, January, February average because, as I mentioned before, that's one of the active seasons for atmospheric rivers. So here we're seeing the quarter degree atmosphere winds. This is for the present day, and this is for the future, and then this is the future minus the present day. So what we anticipate on the west coast of the U.S. is to have fewer atmospheric rivers in the Pacific Northwest and more making landfall in the Pacific Northwest and more making landfall along the coast of California. And now to look at the same plot, but in the Atlantic Ocean. So again, here's observations. This is the present day, the future, and then the future minus the present day. And so here we see that both the eddy-driven jet and subtropical jet, and I should have mentioned previous slide, the changes were mostly in the subtropical jet. Both of them are increasing and indicating that there will be more atmospheric rivers making landfall in both of the regions of interest here. Okay, so now we're looking at it in a different way because these are actually quite complicated, and what's happening at the 300 millibar level isn't the whole story. So that's really kind of the steering flow. The moisture transport is happening more at the surface. And then what's happening at the different latitudes also matters. So the bar charts that we've been looking at are an average over all latitudes for a particular region of interest. And so here what's been done is that you're looking at the change that might be expected in the future based on our simulations over the different latitude bands and then for the different months. And so the shading that you're seeing here is the percent change in the number of atmospheric rivers that you might expect, with the red colors being a decrease and the greens and blues being an increase. The numbers that are here that are hard to see, but I'll walk you through it, are the total number of atmospheric rivers found in that month for every year of the simulations and for all 3 ensemble members. So what we see here in this case we're just looking at the North Atlantic. For the Iberian Peninsula, it looks like we'll have a decrease in atmospheric rivers at most latitudes and for most months. And in fact, if you look at the total number, so for example, September, this is 282, I think, and it goes down to 193 total atmospheric rivers making landfall. However, these particular months were the months that we had fewer atmospheric rivers anyway. It's the not as an active season. So before, we'd been looking mainly at December, January, February, and so you can see if we look here, we indeed do see an increase in those atmospheric rivers. But it's really important to look at all months and all latitudes, because even in the months where you have fewer atmospheric rivers making landfall, especially looking into the future and thinking about the rivers maybe transporting more moisture in the future, it can really make an impact if you had, normally one atmospheric river in that particular month and now you have two, or maybe you have three, or maybe you go from three to none. And when they can carry so much moisture and it's so important for the water supply in those regions, then this can really make a difference. The suspense is part of the presentation. So this is kind of a teaser for future work. So this was using the 10th degree ocean simulations and comparing them with the 1 degree ocean simulations. And so Christine and I have actually started working on this, and our thought process is that the ocean conditions underlying these atmospheric rivers must make a difference. And this is sort of proof that it probably is making a difference. And so here, this is looking at the Atlantic Basin. The bottom plots are the Pacific Basin. On the left-hand side are atmospheric rivers overlying the 10th degree ocean, and on the right-hand side, it's the 1 degree ocean. And so what I wanted to point out here is that the smaller scale features that are now being resolved by the 10th degree ocean are really imprinting a signal into the atmospheric rivers. This one might be a little bit more easy to see. So you can see a lot more structure happening within this atmospheric river than in the one with the 10th degree ocean. So this one's just much more smoothed out. And so it kind of makes sense because the moisture transport, everything kind of depends upon what's happening at the ocean surface. So the sea surface temperature, the fluxes between the atmosphere and the ocean are going to impact these atmospheric rivers. And so we were pretty excited to see that there really was a signal here, and so these are things that we're going to be looking at in the future. So in summary, atmospheric river location and strength has been tied to the atmospheric jets. So those making landfall on the US West Coast and Iberian Peninsula track the subtropical jet, and those making landfall in the UK track both the subtropical and eddy-driven jets. Using higher resolution atmosphere does improve the representation and statistics of the atmospheric rivers, and this is due to the improvements in the position and strength of the atmospheric jets based on the increased resolution. The largest changes in the number of atmospheric rivers occur in their active season, whatever season that is for the particular region. And in December, January, February, which is the active season for the atmospheric rivers in all of those regions, we anticipate a decrease in the landfalling atmospheric rivers in the Pacific Northwest and an increase in the other 3 regions that we looked at. And again, this is due to changes in the atmospheric jets.